starting out bad. Hello, welcome to week 16. Last week of the semester. So we have our last project due this coming Sunday, the 11th. And then we have one more week of new content since I don't give a final exam. Good morning, EdCast. Nice to see you as always. Thanks for being here. Anyway, so the last week of the semester, we will talk about hash tables so that you kind of leave with one more piece of content that you will find references to, especially if you go on to like Programming Algorithms 3 after this. So you could think of it as bonus content, but next week will be one more normal week. This week is the last not normal week because we have lab discussion homework and then also a project. The last two labs have all been about building the binary search tree that will be used in that form that the labs created it for the final project. This week, the lab is the last piece that you need for the final project. So all of the work that you've done for 3 weeks, including this one on labs, is code that you should plug straight into project 4. And then the only thing that's left after that is to create the driver. Hopefully some of you have already started that, but if you haven't, same kind of setup as we had on project 3 with a file with input commands in it, and then you need a driver that handles all those commands and behaves according to the spec. So I'll talk about that before we finish today. Okay, so I wanted to show you, for those of you who want to practice your skills, there's this thing every year called Advent of Code. It starts on December 1st and goes through December 25th. I personally have never been around on the 25th. I think last year I got to, well, we can look. How far did I get last year? Last year I got to day 17 before I got tired. So this year, today's day 5. Anyway, these are good puzzles. Some of them are easy. Some of them are quite difficult. They're all good for practicing input processing, choosing correct data structures, creating structs and or classes to model the data, and then algorithms that solve problems. So it's free. So if you're looking for a place to kind of keep your skills sharp or further sharpen your skills, I like Advent of Code. You can go back to any of the years since 2015, and the old years should be fully unlocked. So you can just go do those puzzles. The answers are supplied for you. Anyway, good place to practice. Okay, so let's just get into our content for this week. So we are talking about operator overloading and friend functions. You need these things. You need both of them for your project. The code we're working on this week is called the Word class with the capital W. And to complete it, you need to know how to overload operators for it, and you need to know how to implement a friend function for it. So we will start by talking about what those things are and what they look like. And then look at a kind of parallel idea. So I'll do something very similar to what you're going to do in lab, but I am going to leave you to do the actual lab this time for yourself. So operator overloading, what does that mean? Well, let's start by making a class. It can be a struct, doesn't matter. I'm going to use a class, but I will call it, I don't know. I'll call it a food item, I guess. Sure. So I'm not even going to put any data members in it to start. Well, I'll put one. All right, so hopefully everyone gets the idea here. food string using namespace standard. Okay, so we have this class, has one data member. I have overloaded the constructor. By the way, if you have an overloaded constructor like I do here, you can no longer make default food items. So once I have implemented a constructor, I don't get the free default. So you'll see a whole bunch of errors, but they're all related to no matching constructor. So if you have a constructor implemented, you no longer get the freebie. So I'll just call this apple. So I can construct food items with a name. All right. So let me make a couple of food items and then talk about this overloaded operator thing. Banana. So if f1 greater than f2, I'm going to need a getter for that. Let me do a getter here. When you put a const, by the way, on a member function like getName, what you're saying is you want the compiler to sort of have your back and prevent you from making any accidental overwrites. So we will often put const on functions like this just so that if me, the programmer, happens to accidentally do something dumb, like so this keyword const here, no viable. But anyway, the error that's interesting here is const standard string. So this const here makes it so that I will not be allowed by the compiler to make this change. Now, why would I do that? Why wouldn't I just be careful to not make the change? Well, sometimes you get busy and you make mistakes. So keyword const is really just there to assist you, the programmer. So as you are building something out, if you flag it with constant, you are saying if at some point in the future I make some dumb mistake, like overwriting the name when I just mean to be retrieving it, I want the compiler to step in and stop me. So that's a good thing. We like that. And if I were to take that const off, I'll still get errors because of the operator thing, but I don't get any of the errors about that const string anymore. So const is just there to help you protect yourself. So I don't want to make changes, so I put const on it, and that way if at some point I'm not paying attention and I do something dumb, the compiler's going to step in and say, you said you didn't want to change stuff here. So that's a good way to protect yourself from mistakes on your getters. All right, so now the actual error. I want to compare F1 and F2. I want to see if F1 is greater than F2. I get an error immediately saying invalid operands. What C++ is telling me is that it doesn't know what it means for one food item to be greater than another food item. Why not? Well, the reason is because I just created this data type, and there's no way that the compiler could possibly have known that some point in the future I would create this food item class and want to compare it. But it would be convenient to be able to compare them. So I have the ability in C++ to overload operators for my custom types. So if I want the operator greater than to return a result on F1 is greater than F2, I can implement one. So I will go up here into my food item and I will implement one. So that's how you reference the greater than operator is operator greater than. They return a true or false, greater than operations do, right? True, it's greater than, false, it's not. And then what's hard to see here is that you have the this object, food item object, and the other food item object. This is one of the harder things to understand. So where's the other food item in this equation? It's the this, which in code is the one on the left. So the one that is unreferenced here in code is F1. It's the left-hand side of the operation. The argument one comes in from the right-hand side of the operation. So when I say this name, I'm referring in this specific example to F1. So is F1's name greater than F2's name, other's name? Which will be F2, which is banana. So notice what I've done here is I have overloaded this greater than comparison operator so that it becomes a comparison of the two names. Now these are strings, but strings also overload this operator. So the C++ string will do basically alphabetical order respecting upper and lowercase letters, which is called, what's that word for describing the actual order that's not alphabetical? I'll think of it, doesn't matter. So I am redefining for my custom food item type the meaning of greater than to be the thing on the left's name being greater than the thing on the right's name. And now it works. It says banana is better, which by the way, it says that banana is greater than apple. But the string, if you read the string class and you look at operator greater than for strings, it'll say whatever that order is called. Anyway, comes after, right? But we can also do something like this. Let's say that we had, calories. So instead of the names, I could compare the calories. It's totally up to me when I'm overloading an operator. I have to decide what it means to order, to put in order two items of my custom type. So what does it mean to put two food items in order? It could be that I compare the calories. It could be that I compare the names. It could be that I compare the names and the calories. That's completely a matter of how do I want my custom food item types to be ordered when they are compared with a greater than. We got to give them some calories. So we know banana came first, but let's give, I don't think this is actually accurate, but maybe it's a very tiny banana. So if I have overloaded the greater than operator now with calories, apple should come first. So that's a greater than. Now I'm going to show you the alternative to doing this before we talk about friend functions. So let's talk about, let's actually put a counter in here. Amount consumed. That's getting too long. So when I get a very long initialization list, I'll usually put it on the next line down. So amount consumed. Yeah, I'll worry about that in just a bit. So we could order on that as well. Okay, so here is an overloaded operator using the embedded this pointer, which would be the thing on the left-hand side. You have the option of doing this in a different way. You have the option of defining operators so that the two food items. The two food items in the equation are actually passed in as two separate arguments. Now this does introduce a complication which we're going to address here in a moment. But you can, instead of making the overloaded operator be a member of the food item object, which means that you use this being one of the sort of implied arguments, you can make the function work as a non-member and accept the left hand and the right hand side as its two parameters. Now that's should cause errors. That causes errors. And the problem is yeah, so we'll fix it. But anyway, you get a bunch of errors because C++ doesn't know what to do with this situation. So this is what friend functions are about. So a friend function is not a member function, meaning it does not have access to the this pointer, the implied sort of calling object. A friend is simply a function that has privileged access to data members of that class. So as the friend, which is embedded in the class, but it's called a friend, it is not a member. It's actually a non-member function that can use the objects and directly by dot notation access their private data. The sort of off-color way that I have traditionally said this is that friends can see your privates, which is not a very nice way to say it. But friend functions, they are not member functions. You don't call them with objects of that class. You call them with arguments that are objects of that class, and the friend keyword gives that function the ability to use dot notation and access private data members directly. That's kind of complicated. I think it'll work now. Oh wait, righty dot colors. Okay, so I get the same result, and I have these two options sometimes when overloading operators. Now, I happen to think that friend functions are harder. They're harder for me to read and understand. So I prefer the member style where you use the this as the left-hand side of the operator. But we are going to see a situation where we don't have that option. We have to use a friend. So anyway, you can implement most overloaded operators, all of them. Probably all of them. As no, I say most. You can implement most overloaded operators as friend or as member. This is just two different ways of doing it. I happen to think that the member style is a lot easier to read as long as you understand that you can't see the left-hand side of the comparison. It is the this object. So the this is on the left. Okay, amount consumed. Why is that there? Yeah, okay. So, and we can do a whole bunch of these, right? So we could say that less than is that this calories is less than the other's calories. We can do greater than or equal to, not equal to, equal to. All those comparisons are relatively easy if you understand that you can't see the left-hand side when you're implementing the member functions. You have to just know that when it's called, there's going to be one on the left, which is the this object, and there's going to be one on the right, which is the other object, which comes in as a parameter. So it's a little weird, but these comparisons are not too bad. What is bad, though, is if we wanted to do this. If we want to just see out the object directly. Now I'm going to get all kinds of complaints about this because C++ is going to say, I don't know how to do a food item on an output. I know how to do strings, I know how to do ints, but I don't know how to do a whole food item on an output. So we can overload that operator as well. It turns out it's this thing right here. And it's a very weird one. And it is one that you want to do as a friend. So the way I overload that operator is I make it a friend. It actually returns, it just kind of adds data to a flowing stream of data, which is why the return is a reference to an output stream. Looks very weird, but if you think about it, I do cout, operator, stuff, operator, more stuff, operator, more stuff. What's happening along that chain is that the stream is just kind of building up with more data over time. So that's what this is about. The operator looks like that. No big surprise. And then the arguments are weird because there's two arguments to every stream. There's the place that it's going and what's going into it. So what we want is the output stream. That's a given. So that's the left-hand side always is the flowing stream of data. What we want to put on the right-hand side is a food item. So now we have a friend function. And what does a friend function mean? It means that I have the convenience now of accessing that food item object's data members directly without having to go through getter functions. So this friend function has privileged access to these private data members. But all I'm going to do is I'm going to put stuff on this output stream. So I will put the food item's name. I will put some string stuff on it. I'll just put the calories for now. No, maybe two things. Let's start with that. And then we have to return the output stream after we've added more stuff to it. So this all looks very, very strange at first. But that is what we have done, is we have added more things to an output stream from the food item itself, and then we return the output stream because there may be more stuff in the chain. So I'll give you an example of that, actually. So here's one of those calls. The output stream on the left, cout output stream, the food item on the right. But we can put this in a chain. So we can take this and chain this into an output stream so that it flows into yet more data. I'm going to do the same thing for both. And all I would really say here is figure out how to use this pattern to implement your own overloaded operators. And don't fret a whole lot about the complexities of it, as long as you have some examples to work from. And you can adapt them to whatever class or struct objects you are working with, then you'll be fine. Okay, so let's try it out. I have overloaded the operator, so there's the better, and there is the output of the food item itself, apple, 100 calories. Yeah, I'll leave it at that for now. Okay, so that's the basics of it. I'm going to do two more things with it before we go anywhere else. So one is, what if I wanted to separate out my food item into its own header file and implementation file? What would that look like? So I'm going to do that first so you can see how friend and member overloaded operators get implemented when they are separated out. You need that for the lab. So let's create food item.h, food item.cpp. So I'm going to have a header file and an implementation file. Go back to main and let's get the food item out of here. And to get it back in, we will include food item here in just a moment. Pragma once only on the header file. So what we need to do here is separate the implementations out from the header part. So I'm going to be lazy here and copy these implementations over. Copy them over here, and then go back and do the cleanup work that I got to do. All right, so we'll be back. So let's see, how do we get rid of, so we only need function headers. Yeah, that's fine. I'll go ahead and leave that one behind, just so when you access this, it will make sense. So I took all the implementations out and made headers, and now I got to go fix up the implementations and make sure that I do the scope resolution part. So make sure that this one looks like they're all over. Yeah, they're all shifted over. Shift tab. Okay, so anyway, I got to make sure and do scope resolution on the constructor, on the getter, on the overloaded operator, because it is a member of this overloaded operator. And then for the friend function, oddly, the word friend goes away, and the function does not get scope resolution because it's not actually a member of the food item class. It's just declared in there. So this is just weird, but it comes up a lot when you are overloading operators or reading code where people have overloaded operators. So just heads up, friend functions look really, really strange. So notice there's no scope resolution. I took the keyword friend off because it only needs to appear when you first declare it. And then I have done scope resolution on all the member ones. So member overloaded operators, for our purposes anyway, they're all going to have one argument and then going to use the implied left-hand side of that comparison, which is this, the calling object, as it were. Let's make sure it still runs. Oh, string. I forgot to include string here. I don't even think I need it in main anymore. I don't. Okay, so I had to get string into my food item class for it to work. O stream. Goodness gracious, fair enough. I'll just let the compiler help me out. All right, everybody's happy. So there's the food item header. You will have direct access to this REPL for study as you prepare your lab for this week. So anyway, there's my food item. It's got a greater than or a less than. I'm going to comment out these overloaded operators for a moment. And I'm going to get rid of this main and make a new one. Let's see, what else do I need? I need to comment out all the operators. So I want to get rid of this code for teaching purposes. You're not going to want to get rid of it for lab and project purposes, but I'm disabling all my overloaded operators so that what I do next will make sense. So let's see, I need to get my lab 15, wherein I completed the binary search tree. So now let's put food items in a binary search tree and see what that feels like. All right, So I got my binary search tree from lab 15 in my sample for week 16. Let's include it. And now let's make a binary search tree to hold food item. Make sure that compiles before I do anything else. HPP. Okay, so everything seems okay, but this is why we're going through this whole exercise, is because you are going to have a class called Word, and you are going to want to make a tree for Word and put Word into it. So I'm going to try. I'm going to go ahead and try to do food.insert, and I'll just make a food item right here in place. So let's put apples, and let's put something in the middle of the alphabet just to be more fun. Put orange in there. I have no idea how many colors these things are. All right, so let's see if the orange will insert. It will not. So what is the problem? Notice all the green here. It's saying that this less than comparison operator doesn't work for food item. That's a bummer. That I want to put food items in there, but if I go look at the binary search tree on line 97, oh boy. So this is templated, but I'm feeding a food item into this tree as the T type. And then I'm trying to do comparisons to see when food items are less than other food items. That seems like a significant problem. So how do I solve that? I solve that by overloading the less than operation. I'm getting a complaint saying you can't put things in a tree that you can't do less than on. Fair enough. So I'm going to restore my less than and my less than implementation. And then I'm going to try to compile again. Now it's complaining that it can't compare food items greater than. Well, crud. Or actually, well, lucky because I actually have that ready. I just commented it out. So let me put greater than back into play. And now it will actually insert a food item. So why are we overloading operators for project 4? Because we want to insert a thing in a tree that is not a standard data type. Putting an int in a tree is easy because they already know how to compare themselves. Strings can already be compared. But when we create a custom type and the tree is trying to sort them out into itself, the tree has to know how to compare them. So we have to tell it by overloading operators. So now we can insert stuff. And then let's print it. Print in order, I think it was called. Oh, crud. I knew this was going to happen. So it's telling me I don't know how to print out food items. That's from line 167 of my binary search tree, 165. So let's go look at 165. Yep, there it is. There's a food item trying to be printed, but I disabled the code that would allow that to happen. So let's go re-enable the code. Actually, oh yeah, I did. I took out the implementation of it. So I'm going to go ahead and re-implement that operator so that when the tree tries to print food items, it works. Let's put in a few more. I don't know. Cherry, let's say 5 calories. What's pineapple? That's probably a lot if you take the whole pineapple. Pomegranate. If I misspelled that and you know better, please you can tell me it's okay. And then let's print food.print in order. Okay, so what is the order that it is printing? It looks like orange is in there. Oh wait, no, I have this original print that's messing me up. There we go. So let's see, the ordering should have been by calories. So it's doing by calories, but it makes sense to me that I would want sort of my little item dictionary, if you will. Well, it is. It's magically in alphabetical order because of the calories that I put. So let's put a banana in there and see if we can't mess that up. Let's make the banana be just a little bit more than the pineapple, just to prove that the calories are the thing being sorted, which they are. Okay, so that's right. So magenta, notice it's not in alphabetical order. And why is that? I will show you my sorting routines. Why are they not in alphabetical order, chat? There's my two food item overloaded operators. Notice banana is last, by the way, which means it can't at all be alphabetical order. So you're correct, magenta, and there's a reason based on the way I've coded it. Does anyone in chat see what I have done, that the ordering is as it is and not alphabetical? Good one. So magenta is right in chat. It's because I told it to order on calories. So when the tree is figuring out which way to go, it's using the calories, not the names. So if I change these to be the names, I got to change both for this binary search tree. If I change it to do food item comparisons by name and run it, it will now be in alphabetical order. So I'm in complete control of that. As the programmer of the food item, I decide how this thing gets ordered. It does make sense to order it by its name. All right, so let's add another component and then kind of play. So this is what your project 4 is going to be doing. It's going to be taking strings with some data with them and putting them in the tree. So I'm going to give you one more hint. That'll help with the lab. So let's get the amount consumed into the mix. So I'm going to group up those two operators and put that one next to them. So I'm going to add a new function. And I'm going to say void increment amount consumed. Or I'll just say consume. Consume. Not const, because I am actually going to use this function to do a manipulation. So let's go implement food item consume. I'll put that up here. Void food item consume. And I'm just going to say this amount consumed plus plus. That'll mean I'll eat one more, right? And then I'm going to go update the output operator. And I'm going to add Let's break this up right here. Yeah. You have eaten, consumed. Let me just see what that looks like before we've done any consuming. All right, so now you'll see that they have little counters on them. So now let's do the next step, and we're going to need this for the project. So whenever we consume one that's already in the dictionary, what I want to do when I consume foods that are in my dictionary already is I want to actually update the thing in the tree. So I don't want new elements going into the tree. In fact, if I tried to insert another banana, it might fail. So what I want is I want to be able to get a pointer to a food item by name. Something feels funny. No, that's right. So now how did I even know how to do this food.get food item? Why do I know that a food item goes in there? Well, I could say instead, what happens if I try to get the item with cherry in it? Let's just see what happens with a food.get cherry. So what I'm trying to do is get a pointer back into the tree, and then I want to consume a cherry and see it update inside the tree itself. Okay, so you'll notice here on line 54, it says to get a tea, which is a food item, you have to give me a tea, which is a food item. So I cannot just give it a string and get a food item out. What it says is if you want a food item, you got to give me a food item. All right, well, how do I do that? Since I'm trying to get the actual cherry that's in there. Well, the way you do that is you make one just a throwaway food item. I have to also give it an amount of calories. So the way this is going to have to work is I'm going to have to feed a food item into the tree to get a food item, a pointer to the food item that's already there. So think of this food item as kind of just a for searching purposes. This is a finding food item to get the actual item that's in the tree. So I'm going to have to build a food item and pass it to the tree, and then the tree hopefully will go actually find the food item that has cherry in it and give me a pointer to that cherry in the tree. I never tried it. Okay, so it is actually finding it, which is fortunate. If we go look at the get, let's see the process that the tree actually used to find the spot. It was using the less than and the greater than to figure out where the cherry is. So I actually got the cherry in the tree, and the reason I'm doing that is to show you for your project's purposes. So I have to have this kind of throwaway item to perform the get in the tree. And then I get the actual item. And with the actual item, which is F, I can consume one. And then I'm going to print the tree again. And what you should see is that I've consumed one now. So there, notice I have eaten one. Now, it doesn't make sense to me that I would have a food item in the tree if I haven't eaten one. And this is also true on your project as well, and the lab, I think. So I'm going to go ahead into food item and say, you know what? You probably wouldn't create one unless you had just eaten one. So let's see what that does to the program. All right, so now to be in the tree at all, you automatically eat one. And then when I consume a cherry, I actually use the throwaway food item that has cherry, which helps me locate the item that has the name cherry in it, and then I can update the one in the tree. I hope that makes some kind of sense. I'll go back and look at the code. So this code right here gets me the cherry food item that is in the tree. It gets me a pointer to it, and using the pointer, I can actually alter the item that's in the tree. Now I need to be very careful not to change the name of the food, or I'll break the whole tree since it's sorting by the names. But I can use this get function to go into the tree and do small updates. It should also be true, by the way. I'll reuse that F. So what if I try to get, so here's another throwaway item. So I want a kiwi. I have to give it 2 arguments for that to work. So can I get kiwi? Should be true. That F comes back null in that case, and it'll say sorry, no kiwi, which it does. So sorry, no kiwi. So that's a giant hint for the project right there about how to work with this tree. And then one more giant hint. So here's what the sequence should look like in your project 4. What should happen is you do this. You say, I'll get the pomegranate, throw away food item, because that's what I have to give it to do a search, pomegranate. So when you do a throwaway object like this, because that's what the search is going to need to find a matching object by name in the tree, if you're required to give it additional arguments beyond the one that really matters, which is the name, just put zeros or just garbage data. It's fine. Now, how do I know that this get function is going to use the name of this throwaway food item? I have to do a long trace of the code. So let's go back and do that. So how do I know that the get will actually end up using the name to match the throwaway pomegranate with the pomegranate that already exists in my tree? Well, I have to go to tree and look at get. So I look at get and I try to figure out how is the tree locating the spot. It is moving left and right based on the food item, which is the T in this case, being less than or greater than. Okay, so the tree doesn't actually know the name of the food item. The tree has to wait for the food item itself to do less than or greater than. So if I go to the food item and I look at less than or greater than, I will see, oh, it's matching on the name. So that throwaway food item, I have to give it the name I want, and any other data to fill in the blanks don't matter. And it's going to find the match by the name. So that's not easy stuff to do. Okay, so anyway, that's how I know. Because I trace the code first to the tree, where I realize that the tree doesn't know. The tree is just calling the food item's own comparison operations. So then I go to the food item and I see how the comparisons actually work. Oh, it's comparing the names of food items. Okay, so how would I handle an insert? How would I handle a possible duplicate of a food item on an insert? Well, the way I would do it is I would try to get the food first, and then I would say if So if I get a null pointer when I try to find the pomegranate, that means that the pomegranate's not there, and I can simply say food.insert the food item for pomegranate. And then in this case, I would need to put whatever the actual calories were that I want. Now, if I get a non-null pointer back, I will update it in place, which for a food item means f consume. So that's how I would do a duplicate, a possible duplicate, meaning every insert needs to work this way. I should always check to make sure that I don't already have the item in place before I try to insert a new one, or I'm not going to get the necessary updates that I want. It should update it, by the way. So if I do one last print here, just take both of those. If I do one last print here, it should show that the pomegranate was in fact updated because it was there. And here it's been updated in place inside the tree using the pointer that the get function gave me. So there you go. That's very close to what we are doing on the project. So I will share, in fact, I'll go put it where I won't forget it right now. I'll share a link to that REPL so you can look it over for the purposes of getting through the lab this week. Yeah, so why do we do overloaded operators? Sometimes because we would like to be able to use them as a convenience. I personally don't like overloaded operators. I think they're confusing. I think they're hard to find in code. I think they're easy to screw up. But C++ allows them, so I think you should be exposed. So the why for me is never because I just want to. The why for me is because I am trying to use some kind of data structure that is trying to order my custom type, and it forces me to do that. So in the case of our binary search tree, if we want to put something in there that's a custom type, like a food item, then I am forced to overload the greater than comparison, the less than comparison, and the output stream operator, which is called the insertion operator, by the way. I'm forced to do that by the tree. So that's a why. I guess that's kind of also the same thing as the when. For me, when I'm forced to. The how is what we talked about in these examples. So if I can do it as a full member, I prefer that because the overloaded operators are simpler when they're written as full members. But if I can't, like with the OStream thing, then I use a friend. That's kind of the how, and I provided examples of those. Actually, let me go ahead and add. Let's go just look at the lab. Together, and I have that link that'll go on the lecture page. So we will look at the lab, and then we will talk a little bit about the project, and then I've got a picture to draw for you to kind of finish that all up. All right, so the lab. So we are, by the way, while I'm here, we are in week 16. So the project is due on this coming Sunday. And then next week we have a normal week with some new content. Hopefully you'll all choose to consume it, but some of you may already have the points you think to ignore me on week 17. That's up to you. I find them interesting, so hopefully some of you will join me in that work. But anyway, this is the big week with the project due at the end of the week. Lab. So the lab is very similar to what I just did. And I will tell you right now that what your project needs is your bstree.hpp and word.h and word.cpp from this week's lab. You are building a thing that you need exactly as it is built for the purposes of your project for. There may be some extra things that we don't necessarily need in here, but you need it for your project for. So what is this word class? It's a little confusing because it's a container to hold a string and a counter. And I'll draw a picture to make that clear to you. There's also, by the way, this uppercasing function that will help you with some of these case insensitive operations. Let me see if I did the to upper for you. I didn't. Maybe I'll do that in my little sample REPL. Okay, so what are you doing in this week's lab? You need to properly initialize the big W word with an empty string and a counter. So kind of like my food item with consumed, these are going to be words, strings. They have a counter associated with them. And what your tree is going to do is it's going to, every time a new word that's not already in the tree appears, it will be inserted in the tree. Every time an already existing word appears, you will not insert it in the tree because the tree won't let you do that. You will instead use a pointer and increment the count of the number of occurrences of that word in your tree. We also have an overloaded constructor that has a specified word. Notice, by the way, that you should start with a count of 1, just like I did with food item. Converts the string param to all uppercase. All right, so very, very important. Convert the string to all uppercase. I'll probably go do that in my REPL to help you out. Get the string that is the word inside of the big W word. Get the counter. Increment the counter, just like I did with my food item with consume. Overload the equivalency operator. We don't need it for the project, but you do need it for the lab. And it's easy and it's practice, so why not? So that's a member. You can tell that because there's no friend word in front of it. The less than, the greater than, rather, the less than. Notice it's going to be lexicographically, that's the word. It's going to be comparing the string part, the little w word in each big W word object. Here's a friend. So that's how that's set up. And then we have this to string. So let's go make one of these and then show you how I would use it for my food item. So I'm going to go ahead and add that just like it is in the lab. Add that to my food item. And then I will go implement it in fooditem.cpp. I think I'll leave that friend function down there by itself. And make sure that I food item it. Okay, so take a string and make sure it's in all uppercase. The easy way to do this is to make a string, call it the up string, I'll call it, and then I will loop through the original string, pulling each star out, and simply concatenate the upperified version of that character and then return the ups. So the ups is built by concatenating all of the uppercase letters from the original parameter string. So how would I use this? I would use it like this. When I do these comparisons, I can say I can upperify things. And if I do that, now it's case insensitive, so it doesn't matter if someone just made a horrible mess of the whole thing. I'll go show you an example in my little program. So this is now case insensitive. It doesn't matter if the words are spelled differently, and let's just go do an example of that with the pomegranate. So with the pomegranate, if I do this, O-M-E-G-R-A-N-A-T-E, it won't matter. because the comparisons are going to be done as all uppercase letters. The pomegranate will still have 2 eaten in it. So that's what we mean by a case insensitive comparison, is by making sure everything's upper. Now in the lab, it said the constructor says convert the string to all uppercase. And it also says that in the set word to convert the string to all uppercase. I'll just show you one example of that. So here, it wants the name in all uppercase, which means I'm going to have to go into the block for that part, this upper, that N. So now the food item being stored in the tree is already all uppercased, and let's look at what that would look like. I broke something. Oh, I'm a dummy. This name equals the uppercase of that thing. There we go. So now what's in the tree is all uppercase. And if we get a comparison coming in, we don't really have to do the this upper here, but I probably would leave it just to be on the safe side that the comparisons are being made case insensitive by being all uppercase. Okay, so that will be, all of that will still be, in fact, I might say, leave a note there. So assuming that you've been careful with your constructors, that they uppercase the string as you're building the food item object, and that you are uppercasing should you have a function that allows the name of the string to be changed, then you shouldn't need to do this, but this does make it just absolutely safe. So this is completely case insensitive. So that's what's being asked for here on the equivalency, on the greater than, and on the less than. They all say case insensitive, which means that you need to implement and then use this upper function to pull off case insensitivity. It also says on this constructor here, convert the parameter to all uppercase. Also on the set word, it says convert the parameter to all uppercase. So several places where you can use that. Okay, so that's what's going on. We've seen examples of just about all of that here. And then the .cpp file, you've seen how to do that now. Be careful of the friend function because it's not a member. It doesn't need to be scope resolved. And then last thing, and we'll probably get through a little bit early. No. 2 last things, probably. Project 4. So it's going to be very, very, very similar. I did upload a unit test, but just like last project, if your functions don't match exactly, but this time they should, because the labs told you what functions to have and how to make them. So in this case, the test probably will work for you, but it's the same setup. So you have a file describing the required operations. It's a lot less than it used to be. This time, by the way, we're not parsing integers. They're just strings coming out because that's what goes in the tree. Required outputs, same kind of thing. And then a sample input, you should make your own. This one's fairly extensive, but you should make and share your own sample inputs, which are designed to break things. They shouldn't break things, but you should try to set them up so that they could break things. And that's what you want to do. And then we also have a sample output. Okay, so two tricks to help you, and then maybe a little bit, and then I'm going to draw a picture with some pseudocode. Okay, so what you should be doing as you are developing your program is you should be using the sample inputs and then comparing your output against the sample output. So how do you do such a thing? How do I compare my output to the sample output? If you go to the source homepage, hopefully you all saw this on the last project, but there is an announcement here. It's still on the announcements. And it says, try this. So let me show you a thing. If you didn't see this and didn't try it for yourself, so I didn't want to overwhelm people on the last project. You had enough to worry about, but now we can get a little bit more sophisticated. So what I would do is I would take the sample output and I would plug it into this online tool. And then I would take, and let me just jimmy some up real quick. Then I would take my output and I would plug it into the other side, and I would see where and where not there are differences. So let me just make a couple of differences just to show you what that would look like. So let's do, where's the search? Replace. So let's misspell instance in this file. So let's say I made that typo. Hey, it didn't do it, did it? Replace. Oh, yeah, because I did replace it correctly spelled with incorrectly spelled. Place all, there we go. So anyway, if this were your output, and we compare, so what you'll get is this little report, and all the green stuff is good stuff, except for what happened. Something funny seemed to happen. Let me start over. And then I'll get this one. Go away. Anyway, when you do this comparison, you're going to see where the differences are, because it's going to, so you have to remember that the one I want to match is on the left, the one I made in my code is on the right, but I can pretty quickly see in this case, I misspelled instance, and that is causing a whole bunch of mistakes to happen. So that's the first kind of tip about this. Use this online diff tool to compare the sample output and each other's output with your output and see where the differences are, and then go back and figure out where you made a mistake, fix your code. The other thing I would show you, I'll do it here in my, well, I'll do it, let me get a different REPL. It's way down here. Here we go. So how do I get my output conveniently? So you can do this. So you've run it, right? So usage file name, you should all have that. But if I say /main input.txt, I can actually redirect the output to a file instead of to the screen. So I'll just do this. And then I get a file over here called Boyd's output. And then I can copy and paste that into the diffing tool against the sample. So make note of that. Spread the word. This is a new technique that I don't, I always kind of hesitate to throw too many at you at once, but we have time to kind of talk about this today. So you certainly could copy the text off the screen here. That's fine. But some of you might find it a little bit easier to run the program with an input file and then redirect the output to a text file that you can then go open. You can then go copy it, and then you can go paste it. This is going to be way wrong, of course, but then you can go paste it into the diffing tool and see where the differences are. All right, so then one last thing, which is kind of a pseudocode kind of thing. So anyway, there's an announcement, tool to test project 3 output. Still has that link in it. You can share it on Piazza. You can ask me on Canvas inbox, and I'm happy to remind you about it. Last thing on project 4 is going to be a drawing. Okay, so just because I'm sick of working in code, but I also want to be able to draw a picture of the tree. So if your program sees this, right? So you're going to have somewhere in else if command at 0 equals the insert command, then I need to get the rest of that line, because the input lines are going to look like this. All right, so that's going to be in the file. So if the 0th character is an I, then I can simply grab the word, which is starting at position 2, and everything else. So now I have this W. Now there's 2 ways I could do this. The way I would do it based on the word class we were just looking at is I would say word. I shouldn't have used that W. Let's use an S here, because I want to say word little w S. So I'm going to construct a word object with that string. And if you read lab 16, you will see that what you end up with is a word object that has hello in it and then the counter of 1. That's what that will build. And then you say I'll say pointer to a word. So I'm going to pass in this word object to the get, which it will either return me null because this wasn't in the tree, or it will return me non-null, which means it was in the tree. So then I can check. I need to get this to go away. So if that pointer that I get back is null, then I will tree insert that word object W that I used to look for it. If I don't find it, then I will insert it. Else, I will take the pointer and update the counter. So that then the word in the tree will end up having a count of 2. Hopefully that helps. I just didn't feel like typing this because I had nowhere good to type it anyway. So in your decision tree, in your driver, you're going to come across these insert commands. You need to grab the string part as the substring of the command starting at position 2, 0, 1, 2. So that's the hello part. I construct a word object of it, that hello, which will make a hello with a counter of 1 from this week's lab. Then I will attempt to get a pointer to a word that will have that same string inside of it. So I'm looking for hello in the tree by passing this word in. Is there somebody who already has hello on it? If not, then I'll insert it, the W, this new word. If yes, then I will simply go back into that, use that pointer to go into the tree and increment the counter on that hello. So in the end, you're going to end up with, so here's what would happen if I do a few of these commands. Hello, Apple, Apple. Let's say goodbye. So if this were the sequence of commands, the hello would end up at the root. With a counter of 1, because that's how they're constructed. Apple would end up here. The second apple would discover that there's already an apple in there, so instead of trying to insert an apple, we'll simply increment the counter of the apple that's already in the tree. And then goodbye will not be found, so we will less than, hello, greater than, apple, goodbye. We'll go here. With a counter of 1, because every word that goes in starts at 1, based on what we're doing in lab this week. So anyway, a simple example. Of course, if I did another apple later, it would discover that apple's already there and increment the counter yet again. So hopefully that helps. That's what's going on in the tree. It does not allow duplicates. So it wouldn't insert a hello or an apple even if I tried. It would just fail. So what I need to do is see if there's already an apple there and increment it if it's there, and only insert it if it wasn't already there, which is what I showed you on that other page in the messy code. Okay, so this is what you should get. If this tree were to print, it would print out and look like this. It would say apple 3, goodbye 1, hello 1. That's what it would print, because that would be the contents of the tree. The string, this whole thing, of course, is a word. A word. A word. So where would we use such a thing before I quit in 2 minutes or so? One kind of common use of this kind of thing is a dictionary. So you load in all the words, and or a word counter even. You could use this for a word counter to count how many times hello appeared in the document. You simply populate this tree, and every time you see hello again, you just increment the counter for it. And then someone later says, how many times is hello in this document? You can say, well, I'll go get hello, and then I will produce the count for you, which in this case would be 1. By the way, this more or less is a baby step toward creating a database. So a lot of databases use tree-like structures to store and access information. So anyway, that's kind of where this is headed, is that you are learning how the building blocks of more elaborate data structures that we use for things like databases, where we want to keep the data in some kind of order so that it is quickly as possible accessible, but also have the data where it can be updated in place. So anyway, kind of roughly something like that. Sorry, I left this mess on the screen. Let me get rid of that before I call it done. So that's all I got. So you already have a complete binary search tree. If you were successful on labs 15 and 16, you have everything you need in the binary search tree. If you complete lab 16, you have everything you need for this word object that's pictured on the screen right there. What you will then need is a driver that processes the commands very much like we did on project 3. But this time, instead of calling commands on a doubly linked list, you will be calling commands or mapping commands to your binary search tree. It's a template, so that's similar. It'll be a pointer, a dynamic thing. That'll be similar. But you'll have to exercise the binary search tree functions as opposed to the doubly linked list functions. Anyway, it's very satisfying to get this to work, and most of you already have all of the pieces, the most important piece at least, the tree, and after this lab you'll have the other piece, which is the word class. Then you are ready to go. Okay, I'm going to call it quits. I'm a little bit early today. It's 11:20. Canvas inbox, Piazza, office hours, all of those channels. As always, I'm available. Projects due on Sunday, December 11th. So Magenta's asking on the commands we will use, you will have to create Word objects and use Word objects in your commands, like I did with food item. And you will not be using the doubly linked list at all. When you read the project, you will see that there is only reference to a binary search tree and a word class. That's it. So the doubly linked list is now part of your programmer's library, but it is not something we will use on this project. Hence, the complete absence of references to it on the project. Okay. Have a great week, everybody. Get in touch if you need help. Share if you have problems in Piazza. That helps a larger number of us at once. So yeah, I'm happy to answer that. So D. Hawkins asked, where do I source my music? So I use Epidemic Sound, which I pay a monthly fee, and then I can use their music in my live streams and my videos. So they're called Epidemic Sound. And they have a lot of stuff, a lot of stuff. Thank you. I appreciate it. I like it too. Yeah, good stuff. Okay. Anyway, get in touch if you need help. Get on Piazza, and that way more eyes get to see it to help, and more eyes get to see it to benefit by the help. So take care. I will see you next week. We will do hash tables, and you will be past the point of your last project. So hopefully you will come into next week feeling a little bit more relaxed, and we will talk about hashing algorithms and hash tables as a way to close out the semester. All right. Have a great week.